In the next two lab section, we will discuss on the Verilog model, like this part 3 and part 4 are mainly focused on the syntax of various statement in the Verilog model that we can use in our project. There won't be on any live demo or such that, but this is just an review of what you probably already know by doing your project 1 and part of the project 2 so far. This is just an official version of those syntax review part. So let's start on this. So we already know about the blocking and non-blocking procedural assignment from our previous lab slides. We have to discuss this 5 different area as a whole. We have done the blocking non-blocking procedural assignment already. What we do today is initial and always block a little bit, and the timing control on that block. Timing control means like when that blocks are activated and whatnot, stuff like that. Then I think in the next section, that Verilog model 4, we'll look at the syntax of if then else, case statement, looping, some common tricks there, and so on and so forth. So once we've done that, we are practically done with the Verilog model. Whatever we want to know and whichever will be needed for your project implementation purpose, those will be all covered. So we have seen these initial blocks. We have seen this little piece of statement, like we have, let's say, a stimulus module, some register, some initial block, this m equals 1b0. Then what we do here is, I think, yeah, so basically the first one is showing you that this is just a one statement initial block, there are no multiple statements, so we can get rid of this begin end. Begin and end is needed only if you want to enclose like multiple such statement, behavioral statement in one block. Otherwise it's just initial and this one statement, that's fine enough. Next one is showing like, well, I want to do a block which, this is a delay syntax. We know that after 5 nanosecond, hopefully the time scale was given at nanosecond by the backtick time scale construct, which usually appear at the very top of a test bench file or any file that is included in the test bench file. In our case, it would be like, I believe it is proc_definition.v file, which has this backtick time scale definition. Just look at that file and it has defined something like 1 nanosecond by 10 picosecond, something like that. The first 1 nanosecond, that means whatever time I am producing, like by this hash after an integer, after that an integer, it is that much nanosecond. So anyway, so this is saying that okay, after 5 nanosecond we set a to 1, and from that point after 25 nanosecond, that means 5 plus 25, 30 nanosecond from the very beginning or initial, it sets b equals 0, which essentially gives you another indirect information to us that all the initial blocks are executed at the simulation time 0. Okay, so it starts the blocks execution at initial time at 0. Then after that 5 nanosecond, at 5 nanoseconds 0 plus 5 is 5 nanoseconds setting A. After that event occurred, then after that wait 25 nanosecond and then set B to 0. So that means from the beginning it is plus 5 plus 25, which is 30 nanosecond. Okay, so that is the little concept you need to be very clear of. It is not that from the beginning after 5 nanosecond you do this and from the beginning after 25 nanosecond you do this. No. So from the beginning this statement will be executed or will be kind of simulated after 30 nanoseconds from the beginning, because I have already a blocking statement right here which is executing at 5 nanoseconds. Okay, the other concept you want to take from here is the multiple initial blocks. This guy has multiple initial blocks. All these statements are, all these blocks are run in parallel. Okay, so remember that Verilog is essentially a parallel language, and we have some analogous comparison with this MPI programming paradigm and threading programming parallel program paradigm. So this is pretty much kind of reiteration of that statement. Another, these things we have already said that, okay, if there is a multiple statement, that must be grouped within begin and end block. Otherwise, if it is a single statement, just don't care about the begin and end. Okay. Now, the always block is the similar thing like the initial. Always we can do one-liner statement, and we can also do like always begin end for every. It means that always is kind of a while one in the similar loop, like it's kind of starts at time 0 and keep on executing that block. So let's see, out is set to 0, so at the time 0, then always, so it's looping on this little block that delay 5 nanoseconds. So you give delay 5 nanoseconds and make the current output value of inversion of its previous one. So out equals inversion of out. So for if, that means each 5 nanoseconds, so 5 nanosecond, 10 nanosecond, 15 nanosecond, 20 nanosecond, and so on and so forth, out, the value of out will be not of it. Means 0 will become 1, then 1 will become 0, 0 will become 1. So essentially this becomes a clock generation. So if you look at the project to clock generator, exactly kind of this code is there. Okay, so that's the always block. And always block with timing control is something like that we have already seen, that always then we are supplying some constraint there, that at positive edge of clock or in, which means like either execute this block if it is either a positive edge of the clock, means clock is rising from 0 to 1, or value of in is 1. Value of in is true, not at the positive edge, but when it reached that logic value of 1, at that moment you execute this block, always block. So we have also the negative edge concept, so which means this block will be triggered at the negative edge of that corresponding signal. We can stick this, or you can just put another condition like positive edge of clock or in, or negative edge of reset, or in 1 or in 2. So you can actually go and chain with the or condition. Okay, with this when this block is executed, basically controlled by those lists. On a side note, this node, I believe this list of signals in this condition list is called a sensitivity list for that specific block. Just a theoretical side note for you guys. So I think that's all for this part of the behavioral model 3. Then we'll look at more on the decision statement and looping in the next section, which is after that, which will conclude basically our study for the behavioral modeling in the Verilog. And we are pretty much ready for everything to be done at the project 2.